if they use Windows.
Understood. Okay. Okay, I think it's working. Yeah.
Okay.
It's moving up and down. Yeah.
And
Sounds
when
good.
you're done, if you can then just put it back in the little case, bring it down to me.
Mhm.
Okay, perfect.
Sounds good. Uh-oh. You go down and grab some markers.
I couldn't reach that high.
Yeah, that's fine. No worries.
I tried my hardest.
Yeah, yeah. I will need a big white space towards the end. Let's try to extend it. Okay, people are coming in on Zoom as well. We can get started soon. Sounds good. Hi, everyone. Welcome to DSCoV. My name is Andras Zsom. I'm an assistant professor of the practice at the DSI, just one floor down. And today I will talk about decision trees and random forests. These are very powerful machine learning techniques that tend to perform very well on structured data sets, like any kind of data set that you can have in like an Excel, CSV file, or a SQL database. It works really well in most cases under such scenarios. I hope people on Zoom can hear me all right. I try to keep an eye on the chat, and if there are any questions, I will answer it. Okay, so I have some learning objectives for you all. So I hope that by the end of the seminar, you will be able to describe the motivation and the basic properties of decision trees. We will briefly review how optimizers work for decision trees, and we will also apply everything that you have learned here, and there will be an interactive exercise at the end. So let's get started with the first one. So I'm a dog person, so the toy data set we will use in the first half of the seminar will be about dogs and dog adoption. We will try to answer the question up there: will a dog adoption be successful? And if you adopted any animals, you know that there are lots of attributes that can affect the matching between the dogs and the owners. We will focus on 3 properties today. We will have 3 features. First one is the owner home all day? Yes or no? Is the dog a puppy? Again, yes or no? And is the dog spayed or neutered? Again, yes or no? And 6 pups you see here, they are all local dogs. If you go to the RI SPCA, you can adopt them. And I think they have even more than 6 dogs up there right now. So please check out the website if you are looking to adopt dogs. So this is our very simple data set. So we have 3 features. Each feature is binary, true or false. And so they are colored, blue is true, red is false. And we have the last column, which is our target variable, right? Is the adoption a success? So we have 6 samples. We follow what happens maybe a couple of years after adoption for 6 dogs. And if it's success, the true target variable, the target variable is true. If it was a failure, maybe the dog was returned to the shelter, the target variable is going to be false. So this is historical data that we collected, and we will try to develop machine learning models, decision trees, and random forests to try to predict this target variable accurately based on the 3 features that we have available. So far, so good? Okay. So the way you should think about this is that we have 3 features, 6 samples. You can think of these 6 samples as 6 points in a 3-dimensional space. So let me draw that here. So we have 1, 2, 3 dimensions. Maybe the first dimension is the owner home. Second dimension, is it a puppy? And the 3rd dimension here is the dog spayed or neutered? Again, a question mark. And as I said, each of these features can only be a true or a false. Okay? So can someone tell me how many unique data points we have in this data set?
Number of codes times the number of rows?
No. How many unique data points we can have in this 3-dimensional space? Yeah. 8. Don't fight, kids, don't fight. So we can have 8, right? So each feature can be a 0 or a 1. So the owner home can be 0 or 1. Puppy can also be 0 or 1. Spayed neuter can also be 0 or 1. This can here, this one go up here. So what we will have is a unit cube, right? And so we have 1, 2, 3, 4 points here, and then 1, 2, 3, 4 points back there as well. So altogether we have 8 possible points, right? We have 3 binary features. 2 to the power of 3 is the number of unique points that we can have in this data set. So that's going to be 8 for 3 features. And then what we will do is we color these 8 points, right? We look at the data set and we will say, okay, for this data point, true, true, and false, owner home is true, value is 1. Puppy is also 1. We are up here. And then spay neuter is false, so we stay in this plane. If spay neuter was true, we would go up to this point. And so for the first data point, the target variable was success. So this point has a color of blue. And then you can play the same game with all the other 5 samples as well. Let's see, owner home false, puppy false, spay neuter true. Owner home is 0, puppy is 0, spay neuter is true. And then this point back here will also be blue. And in this way, you can just color 6 of the corners of this unit cube, and that will visually represent this data set in a 3D space. Sounds good? Okay, cool. So once we do that, once we color the corners of this unit cube, we can first consider the kind of simplest classification model you can come up with, which are linear predictors. It means that we take a 2D plane in this 3-dimensional space, and we cut this cube into 2 halves. Right? This is called a half space. So once we have a 2D plane in here, we will say that the points above this 2D plane we will predict as true or false, whatever. And the other points below this 2D plane, we will predict the other target variable, right? So we split the 3D space into 2 halves, and we will predict different things at the 2 halves of this 3D space. This is what's called a half space, right? It's one of the simplest classification models you can come up with. And one example is here. We say if the owner is home and the dog is a puppy, we will predict success. Otherwise, we will predict failure for the adoption. So let's see what this means on the figure. Let me delete these colors here. Let's put it black for now. So owner home is true, puppy is true, then we predict success. The owner home, that's these 2 points. And, oh, sorry, 1, 2, 3, 4 points. And then we have puppy is also true. That's these 2 points, right? So we have the owner home is 1 and the puppy is 1. And the spay neuter can be any value 0 or 1. So we have these 2 points. For these, we predict true. For these, we will predict success. Right? And for all other points, we will predict failure, false. So it's going to be red, 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 red. So we have a 2D plane somewhere in here, which kind of cuts off these 2 points from all the other 6 points. So we only predict true for these 2 points, and we predict false for all the other points. Okay, so that's the linear half space. If you play this game, if you check how this model performs on these 6 data points, what is going to be the error? Which points will be misclassified by this very simple model? Yep. False, false, true. There you go. The owner is home. Sorry, the owner is not home. The dog is not a puppy. So we would predict, the model predicts false for this data point, but the true target variable is success, right? So this is the only point which will be misclassified. For all the other points, the classification label is correct. Let's check. First point, owner is home, dog is puppy. So we predict success, and the true target variable is success as well. We know that the second point is misclassified. Third point, again, same idea. And for the other 3 points, one of the features is false, in which case we will predict that there is no success, there is failure, right? And that's exactly what we have for these three cases. Right? This half space is very simple. And even on this very small data set with 6 points, we are not able to find a half space that can correctly predict all 6 data points. So the motivation behind decision trees is let's just make the model a bit more complex. Let's add more rules to it, right? The half space will not always work, but we still want to come up with a model which can correctly predict our points. So we come up with more complex rules. This is just one example. Let's say if the owner is home, the dog is a puppy, we predict that the success will be true. Or if the owner is not home, the dog is not a puppy, then we also predict success. Otherwise, we predict failure for the adoption. If you check how this model performs, each 6 samples will be correctly predicted by that model. So we reduced the loss. Our model was able to learn this small data set. Right? So we just add more complex nonlinear rules, and then we are able to better fit the data set that we have. Okay, let me check Zoom. Oh yeah, okay. Sounds good. It's just a chat. Okay. We'll talk about the exact shape of decision trees in a second, but before we move on, I just wanted to say that there are some pros and cons for decision trees and more complex rules. The advantage is that we have very precise rules, right? So it's very easy to follow what happens and how we should make a prediction for our data set. And it's also interpretable. So you can just write down the rule. If the tree is not too deep, if you don't have too many splits and whatnot, then you can just write down the decision tree on a whiteboard, and you can make sense of it. You will be able to understand how it makes predictions, which makes it interpretable, right? You can check, or a subject matter expert can check whether the rules make sense, right? So these are the advantages. There will be some challenges, which I will talk about soon. We might need a lot of rules to describe the training data. And then the question becomes, how do we represent, how do we organize these rules on a computer so we can easily kind of make sense of the decision tree? And the other one is it might be pretty hard to find exactly the rules that reduce the error on your training data, right? There will be some numerical complexity here, how you can find the tree that reduces the loss on your training set. So we will get back to these 2 questions later. So let's kind of formally define what the decision tree is. I want to keep things relatively simple, so we will assume that we have binary features only. We have D binary features, which means that each sample, each data point, will be represented by a vector. Each vector will contain D numbers, and the numbers can only be 0s and 1s, right? That's what it means to have D number of binary features. And we still talk about the binary classification, so the predicted labels can also have 2 values. In this case, we will say it can be +1 or -1. Right? Those are the 2 possible values your labels. Obviously, when you work on a machine learning problem, you can have more complex data sets. You can have maybe continuous features. We will not cover this today, but if you have a continuous feature, you can binarize it with thresholds. And then you can use this description up here to kind of solve the problem. But any kind of continuous feature can be binarized relatively easily. But we will focus on this one. We will have D binary features in our data set. Sounds good?
What?
Yes.
How would you generalize or reduce the case where you have more than 2 labels, output labels, to reduce it to this?
Yeah. You can do a couple of things. So if you have a multi-class classification problem, right? You have more than 2 labels. You can do 2 approaches. One is called one versus all. So let's assume you have 4 different classification labels, right? You develop 4 models. The 4 labels are maybe class 1, class 2, class 3, class 4. Your first model will be a binary classification model that predicts whether a point belongs to class 1 or one of the other classes. And then another model which predicts whether your point belongs to class 2 or any of the other classes. And you do this 4 times, right? That's one way how you can get back to binary classification. The other approach is where you develop all possible pairs of binary classification. So you have a model which differentiates between class 1 and class 2, class 1 and class 3, class 1 and class 4, class 2 and class 3, class 3 and class 4. So you will have like 4, maybe 6 different classification models. And once you train all those models, you make predictions, you aggregate those predictions, and then you can decide what the final class prediction should be. You can also, there's a third option, you can also develop trees that return not just 2, but maybe multiple labels as well. That's possible too. I think scikit-learn uses the first 2 approaches when you have multiple labels. Yeah. Mm-hmm.
Could also have like the predicted cost of the continuous, right?
Yes, that's right. Yeah, you can have regression as well. Yes, that would be a regression tree. Yes, in that case, I will get back to this later once I have a tree on the slides. But the basic idea is that as you keep splitting your data points, you will end up with a set of points in one of the leaves. And then if you do regression, the predicted target variable will be the average target variable of the points which end up in a given tree. Right? I will have a tree on the slides in a second. I will explain it again. I will get back to this.
Opens up a hole in the blood-brain barrier for physical.
Okay. So the simplest tree you can create is called a decision stump. Okay. We do one split only. We select one of the features, xi, and it's a binary feature, yes and no, right? And we just split based on this one feature. This is called a decision stump. This is the simplest tree that you can come up with. When you have a decision stump in a binary classification problem, the feature you split on xi can have 2 values, false and true, and you have to decide what your model will predict when xi is false and what the model will predict when xi is true. Model predictions can also be yes or no. So you have 4 different scenarios to consider, and you need to figure out which scenario gives you the lowest loss on your training set. Let me show this on the puppy example. So let's take the first feature, whether the owner is home. This feature can have 2 values. Owner is home, the owner is not home, right? Question to you all. What should the model predict when the owner is home? Will the adoption be a success or will the adoption be a failure? Keep in mind, you want to kind of reduce the loss of your problem. Yep. Yes, so we have 2 truths here, and in that case, the dog adoption was a success as well. So it makes sense to predict true on this leaf. And if the owner is not home, you might want to predict failure for the adoption, right? Because that will be true for 2 out of the 3 cases where dog adoption was a failure, right? So what is the total loss of this model? How many points do we misclassify with this decision stump? Yep, we will misclassify this one, and we will misclassify this one. So, right? So 2 out of 6 points will be misclassified. That is the empirical risk. That is the loss on the training set, right? So this is a decision stump. We have one layer That's the green box. And we have two leaves, the yes or no leaves. And then we decided what the model should predict on each of these leaves, such that the error, the loss of the model on the training set is minimized. Right? That's what all machine learning models do, basically. So let's make the tree a bit more complex. We add a second layer, right? We split on another feature. And in this case, we will have 3 leaves on the decision tree. So we say first split whether the owner is home. If the owner is home and the dog is a puppy, we end up in this leaf. We have to predict something. We will figure out in a second what we should predict here. If the owner is home, but the dog is not a puppy, we have another leaf. Again, we will figure out what we need to predict here in order to minimize the loss. And the third leaf is that the owner is not home. And we will make a prediction here as well.
You know this is new, right?
So what should we predict on these 3 leaves in order to minimize the loss on that training set? Yep. So you predict true here. So owner is home, dog is a puppy. We predict true. Yes. Okay, here. Owner is home, dog is not a puppy. The owner is home, the dog is not a puppy. You want to predict false, right? In order to minimize the loss. And for the third one, when the owner is not home, what do you want to predict? To minimize the loss. False, just false. Yep, that's right. Yeah. Because that will get 2 of these points correct, and this one will be incorrect. So in this case, we added an extra layer, an extra leaf, and now this new model correctly predicts 5 of the 6 points. It means the loss is 1/6, right? We could correctly predict this point, which was misclassified by the decision stump on the previous slide, right? So we keep adding more leaves, more layers, and then the model becomes more and more accurate on the training data. If we add another leaf, right? We take the owner home, yes, no. Is the dog a puppy? Yes, no, no, yes. If you figure out, what the predicted classes should be, in this case, you can push the loss down to 0. You will be able to correctly predict all 6 of the data points with this added complexity, with this extra split on the decision tree. So that's the idea behind decision trees. You keep splitting, you keep adding layers and leaves, and then as you keep doing that, your model becomes more and more accurate on the training set. Any questions? Yep.
Sure that spade/neuter isn't causing some effect that causes the training false to occur. Like,
Sorry, what? How do you?
spay and neuter.
Yeah.
How do you know that being true or false has no effect? Like,
You don't. It might have an effect, right? We could have decided to use that feature instead of the puppy feature, right? That's possible as well. We decided not to do that. We just want to kind of reduce the loss on the training set, and we can do that with 2 of the features, and we don't even need to use the 3rd feature. That can happen sometimes. Yeah.
Okay, then you can drop one of those 2 and use the 3rd one,
Mhm.
and you can get a perfect prediction from training data.
Yeah, that's right. Yeah. There are many. You can create multiple trees that will give you a 0 loss. This is just one of the possible trees that you can come up with. You can start with the puppy feature at the top, or you can start with the spay-neuter feature on the top, and still get back a decision tree with a 0 loss. Yeah. Again, this is a very small data set. Only 8 possible points exist, right? So it's kind of easy to work with, but it's good for education purposes. Yeah. Mhm.
Success, false successes, is there any concern that you have success as or just every single observation?
Yeah, we just look at every single, just look at every single observation. Yep. Not in this case. You could change, okay, I didn't say this, but I assume that we use loss or 1- accuracy as our metric to optimize on the trees. You can change that, right? If you care about specificity and sensitivity, you can make that your metric, and you can try to minimize that as much as possible. In this case, I focus on the loss. So fraction of misclassified points, which is also equals to 1- accuracy, where accuracy is the fraction of correctly classified points, right? Yeah, either works. Yeah, sometimes you can switch things up. Okay, so let's talk about how you can optimize trees. So optimization means that you have a data set, you want to get a decision tree, and the question is, how do you find numerically a decision tree which minimizes the loss on your training set? And so formally what we say is that we have this curly H, which is a set of all possible trees that you can create given your data set. And the question is, how do you find the tree, the one tree, which minimizes the empirical loss, the loss on the training set, right? And the other question is, we will discuss later, is what happens to generalization error. If you find a tree that gives you a small loss, maybe even zero loss, how will that model perform on previously unseen data points, on points that the model was not trained on, right? That's what a generalization error means. And that's a very important question for decision trees to consider. So one thing you can do is, when you look for the best possible tree, is that you list all the possible trees, right? And you calculate how well each of your tree perform on the data set, and you pick the one which has the smallest loss. If you have a large data set, if you allow your trees to be very deep with large number of layers and leaves and stuff, this can very quickly become numerically too expensive to do. So this brute force approach is not used in practice. But that would be kind of the naive approach that one could do. You write down all the possible trees you can create, go loop through all of them, and figure out which one gives you a zero loss. If you do this, you will see that your decision tree overfits, which means that it performs very well on the training set. But when you apply it on points that the model was not trained on, then it will perform poorly. It will make a large number of mistakes. This is what overfitting means. And that's a problem, right? We will have to fix that for decision trees. So instead of the brute force search, instead of writing down all the possible trees, what people usually do is what's called a greedy search. So we do not try to kind of in one go find the best possible tree. We build the decision tree layer by layer. And at each step, we try to reduce the empirical risk, the loss on the data set, as fast or as much as possible. So basically, you go through all the features you have. You see, what happens if you split on that feature, true or false. And then you select the feature which gives you the lowest loss if you split on that feature. And that is going to be at the top of the tree. That will be the first layer that you build on. And once you are done, you have two leaves now, right? You go to one of the leaves, you figure out which points ended up on that leaf. Again, you loop through all the features and select the feature which reduces the empirical loss the most, and then you will split on that feature next. You can write this down in an algorithm. It's a recursive algorithm, which always gives me a headache. Recursive algorithms are kind of tough to follow and implement. But basically, there are ways to solve this problem. There are greedy approaches to kind of optimize decision trees. I will not go through this algorithm. I want to get to the interactive example because that's fun, and then you guys can practice how to build decision trees yourselves. before we do that, let me quickly say how we go from decision trees to a random forest. So the basic idea is that you have a training set, right? You select a random subset of the features and maybe a random subset of the data points, right? And you build a tree based on the subset of the data, right? Then you do this again. You select a different subset of features, a different subset of data points, and you build another decision tree. That's going to be tree number 2. And then you keep repeating this, and you build up n number of trees. And each tree is built on a different subset of features and a different subset of data points. What that means is when you select a subset of the points and features, it means that each of the decision tree will be slightly different, right? Some trees will split on a feature, other trees will not because it was not in the subset. The splits will be different, the predictions might be different, right? So each tree will be independent because they are built on a different subsample of the training set. You have a question? Yeah.
Yeah, so just to be clear, we won't use all of the features necessarily.
That's right. Yep. Yeah. That's what we will do in the interactive exercise in a second, right? Yes. You might not use all the features, and you might also not use all the data points. Right? It depends on how you set this up, maybe in scikit-learn or wherever. But yes. So you have n number of trees. You get a new sample, and you run the new data points through each of the trees, and you get back n number of predictions from the n number of decision trees that you created, right? So again, dog adoption is successful or not, right? You have maybe 3 trees. The first tree says that the dog adoption is a success. Second one says failure. Third one says success. What we say is that we have 3 votes from the 3 decision trees, and we aggregate, we kind of average the predictions of all these trees, and we say 2 out of the 3 trees predicted that the adoption will be a success. So the final prediction of the random forest will be that the adoption will be a success. If you need predicted probabilities, you can calculate that as well. Based on the 3 trees, 2 out of the 3 said adoption will be a success. So the probability of success will be 66%, and the probability of failure will be 1/3, 33%. So you can get back predicted probabilities in this case as well from the trees. So this is how you go from individual decision trees, and you create a random forest out of it. Yeah. Mm-hmm.
Like, our like algorithm for each tree is pretty like deterministic. Is the difference between these trees, it's just that like ahead of time, like each tree is like, we are choosing this subset of features and so it'll be different.
Yep.
Or you said it could also be we are choosing this subset of the data.
Yes, you can do both. You can do either, or you can do both at the same time. Yeah. In the example that we will do together, you will use a subset of features. You will use all the points that I give you, but you will use a random subset of the features. Yeah. Yes.
The process of kind of like estimating a distribution from a data set from which you don't know a distribution, the distribution that kind of like produced it, right?
Right.
You take a bunch of samples and then you look at the whole thing, and then that's my distribution. I think they call it
bootstrapping. Yep.
Yeah.
Yeah. It's kind of similar. Yeah. Similar idea. Yeah. You select a random subset features or points or whatever, build a tree, and then you just repeat the subsampling as many times as the number of trees you want to have in the forest. Yeah. Okay. Let's do the exercise. So I have a toy data set. We have 10 samples in it, 10 data points, and we have 6 features, the columns in green at the top. The goal here is to accurately predict whether a person likes computer games or not, right? So the 10 samples are 10 people, And this is what we are trying to predict. 1 is if they like computer games. 0 is if they don't like computer games. Okay. We have 6 features. We know the age of each person. We know their gender. 0 is male, 1 is female. We know whether they are a student or not, whether they are a parent or not, whether they use computer for work or not. And we know how many hours on average a day they spend on the computer, right? This is the last feature. So here is what I would like us to do. I would like you all to form small groups, maybe 2 or 3 people. 1, 2, 3, 4, 5. I would like to have 5 groups, so someone might be alone. I don't know. We will see. So form small groups. And I have 3 dice here. And I will throw the dice for each group. And the numbers on there will tell you which features you can use out of the 6 features that we have, right? Some teams will use 3 different features. If the dice give back the same number 2 or 3 times, that team will use less than 3 features, right? This is how we will randomly select a subset of features. Once you have the features that you can use from the dataset, I would like you all to create the best decision tree you can have using only the features that you are allowed to use. Not all 6, but only the maximum 3 that you have available based on what the dice says. When you build your tree should have maximum 2 layers and maximum 4 leaves. So don't build very deep trees. So keep the depth of the tree at 2 maximum. If you have a continuous feature, you can reuse that feature. You can split based on that feature multiple times. That's perfectly fine. That's something you can do. Once you build your tree, that minimizes the loss on the 10 points. You should also calculate what your tree will predict for the 10 points. Keep in mind that the predictions will be different, can be different from the true target variable. Your trees will not be 100% accurate for all data points. Some points you will misclassify. I know that for certain, this is how the data set is set up. None of the decision trees will be 100% correct. So I will give you maybe 5 or 10 minutes to do this exercise, and then I will collect the 5 trees. I will write down on the whiteboard here what each of the trees predict for the 10 data points, and then we will aggregate the predictions and create a random forest out of the 5 trees. And at the end, hopefully, what we will see is that the random forest is more accurate than any of the individual trees. Hopefully. Doesn't always work out that way, but that's the hope. Okay, so we have some papers and pens here. So maybe, I don't know, you want to be a team?
I can be on team.
Sounds good. You guys want to be a team too? Yes. Okay, I get it. Pen. And there you go. And then you guys get a piece of paper as well. And the pen. So we have 5 teams. Let me go around and quickly tell you which features you can use. And it's very fancy dice. 1, 6, 6. So 1 and 6. You can only use 2 features. Let's see, 1 and 5. You all can also only use 2 features. And you, 2 and 6. Those are the 2 features. And 1, 2, and 6.
3 and 4.
And you guys, 1 and 2. So if you have one of the continuous features like age, number of hours spent on computer, you can reuse that. You can split on that feature multiple times, right? On binary features, you will not be able to do that. So start to work on the tree. I'll give you a few minutes. I need to write stuff on the whiteboard first, and then I will go around and we can check your trees. Make the loss as small as possible. Yeah. None of the trees will be 100% accurate. All of them will have some error. So, how's it going?
We're on the first step.
Yeah.
Okay.
I think
I think it's not
age is the best way to
Age is the
split.
worst, this is the best one to split on the
Yeah.
first.
Okay.
Okay.
Check again. As far as I know, 7 should be the best.
Yeah.
One of those might be.
3 row, a loss of 3.
Oh, I see. Okay. Yeah.
Yeah.
Sounds good. Yeah. Okay. Write on the tree in like the if else kind
Yeah, we
of
just-
statement.
yeah.
Yeah. Sounds good. Yep. Yeah. And then let's see what the labels come out to be. Use computer, age. Yep. Sounds good.
Yeah, it's like,
Yes.
so I think
Yeah.
Mhm.
So.
I did have a
Yep.
question actually.
Yep.
For continuous variables, do you ever, like, is multi-collinearity a for consideration with those kinds of models or?
It can be, yeah. With the greedy search, it's not so much a problem, right? It will select one of the features, and then at the next split, it can use the other feature, maybe. But it's not a big problem. It's a big problem in linear models like regression, logistic regression, and stuff. In trees, they are robust. It's fine. Yep. So you can add one more layer
Yeah.
if you want, and you just reduce the loss.
Yes, side first.
Looking good.
I got both continuous variables, so.
Yeah, you got lucky. How's it going?
We got half of it. Let's go.
Half?
Yeah.
You can make that better.
We're-
Oh, I see. Okay. I see. I thought you have a loss of 50%.
Progress.
Sounds good. Sounds
In
good.
progress.
That's always the most fun.
And then that's through. What?
Oh, I agree.
No, I know, yeah, now we're.
Oh, yeah.
I'm not true.
Let's go, we're doing this.
Uh-oh. Write down the predictions too.
Yeah.
age of 13, zero.
No, 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 no.
Oh.
There will be some loss. Yeah, yeah, some of them, yeah. Yep.
Okay, we're not perfect, we're imperfect.
That's how the dataset is designed.
Oh,
True. So far. Okay, number, gender 1, age 29. False.
Zero, one.
Number 6, 0. Age.
What did you
Where
split
you-
on? What did you split on? Split on age.
False.
Yeah, just split on age at like between 4.2 and 5.7.
7, 0.
Oh, wait,
43.
no, but splitting on age.
True.
You get 4 correct, but if you split on hours, you get 5 correct.
8, 0.
Yeah.
44.
After age.
1.
After
True.
age. Yeah, sorry. Yeah.
So.
Yeah.
Alright, there's only 1.
Yeah.
Everything below is zero.
I think that's.
Not bad.
How many losses?
Yeah, 2 losses.
Okay,
80%, you know
not
what?
bad,
I think if
not
we-
bad. Yep, sounds good. So, yeah,
Yes.
Yeah.
Oh, yes, there's the curve. Never mind. We curved to an A.
no, no, I'm very strict. 80% is a B. No, no, no. Okay. What are your trees? What is the tree? What does it look like? Okay. So
For gender 0, we split at age of 42,
less than 42?
greater than 40.
Okay. Okay. A gender greater than 42 in
age.
this. Oh, sorry, age. Yes. Yeah, that's weird. Age larger than 42, true and false. What do you do with the true side? When the age is larger than 42, what do you do?
We started with gender.
Oh, you start with gender.
Yes.
Oh, okay. Let's start again. So, okay, so you start with gender at the top. It can be 0 or 1.
On a gender of 0,
Yes,
greater than 42,
greater than 42.
false, age bit false.
False, false. Yep.
And then on the right, we split age greater or equal to 29.
Age greater or equal than 29.
False, mixed true, and
Mhm. Excellent. Sounds good. Okay. So what are the predictions for the 10 points?
predict true,
Yeah.
false, false, true, false, false, true, 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 false.
Okay. Sounds good. So I will collect the predictions of the 5 trees in this table. And then for each data point, we will come up with a final prediction. And then we will compare that to the true target variable. How accurate is your tree?
80%. So we got 8 out.
Oh, okay. One of the points might be incorrect. I think 70% should be the max.
Okay, then maybe one of our points is incorrect.
Okay, that's all right. Yep, sounds good. Let me know. Okay, what about you? What is your tree?
I may have cheated because when I binarized, I had 8 less than 10 or greater than 40, so that might be too many.
I see. That's a complex tree. Okay, sounds good. Yeah, yeah. Okay, what about you? Okay. Use computer for work. True or false? Age less than 29. True, false. What do you predict here? Okay. And other side. Okay. True, false. Yep. Yeah, you could. Yeah, yeah, yeah. Okay, so true here and false here. Okay. And then what was the predictions? 0.1. Uh-oh. So let's do it now. 0.1 does not use computer for work, and the age is less than 8, so you would predict false. Oh, you predict true. Oh, I see. Okay. So this one is true, and this one is false, then, right? What? Oh, yes. So you predict true. Yeah, that's what I wrote, right? Okay. Second point, doesn't use computer for work, and age is less than 29, so we predicted true again. There you go. There is some disagreement between the first two trees. Does not use computer for work, age less than 29, another true. Number 5, that's also a, no, it uses, yeah, another true, right? And then 0.5, 1, 2, 3, 4, 5, 29 does not use computer for work, age is not less than 29, so this is going to be a false. And it seems all the other points will be false as well, right? Because the age is larger than 29. Is that correct? Yeah. Okay. False, 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 false. Okay, how accurate is this tree? 1, 2, 3, 4, 5, 6, 7, 70% accuracy. Okay, not too bad, not too bad. Okay, let me delete this. Okay, next tree. What about you guys? Yep. Age is less than 27. Okay. True, false. What do you hear? Oh, we predict true here. Okay.
Less than 4.8.
4.8. True, false.
For true, we said false.
For true, you said false, and for false, you predict true. Okay, sounds good. What are the predictions? True, 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 true.
Then false, false. False, true.
False, false. And how accurate is this tree? 80%. Really? I might have a bug in my code. If you guys, you verified it. Okay, okay, sounds good. Yeah, that's fine. Okay, I need to check my code. Okay, tree number 4. How about you? That's all right. Thank you. Uh-huh. Cool. That's true. greater than 1. Yeah, if that's true, you predict true. Okay. Otherwise false. Okay, and this side less than 2. True. Okay, so if the number of hours is less than true, then you predict false. Otherwise, you predict true. Okay, sounds good. So what are the predictions? True, false, true. And how accurate is this tree? 40%. Nice. That's fine. No worries. Okay, so last three. What do you have?
So we have age, number of hours.
Okay.
Start with number of hours.
1 second. Number of hours. Yep.
Greater than 3.
Greater than 3.
If true, I asked if age was less than 10.
Age less than 10.
True would give a true response, false would give a false response.
Mhm.
On the other side, if age is less than 30.
Age less than 30.
True
True.
gives true response and false gives a false response.
Sounds good.
Yeah.
And then the predictions.
True, false, true, true, and the rest were false.
False, 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 false. And how accurate is this tree?
80%?
80%. Let's check. 1, 2, 3, 4, 5, 6. Oh, wait.
I have an extra.
1, 2, 3, 4, 5, 6,
The fifth prediction.
7.
False.
Oh, this is false?
Yes.
Okay, sounds good. Yeah, okay. It makes sense. Okay, sounds good. So we have the 5 trees, right? And you see that for certain points, the trees give different predictions, right? For point 2, 3 of the trees predict true, but 2 predict false, right? So now we can aggregate the results. Point 1, all models predicted true. Random forest prediction will be true as well. 3 predict true. That's the majority vote. 3 predict true. That's also the majority vote. All true. 4 falses. We have here 5 false. 4 false. True, true, true. 3 trues. 4 falses. And here we have 3 falses. So fingers crossed. Let's see. So this is correct. This is not correct. It's correct. 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 This is not correct. Correct. Not correct. And correct. Wait. Oh, this is correct too? Okay, sounds good. 1, 2, 3, 4, 5, 6, 7, 8. 80%. Okay, well, our random forest has an 80% accuracy. It's not better than any of the trees. But you know, that happens sometimes. But it's still as good. The random forest is as good as the best trees. So yeah, so this is how decision trees and random forests work. Thank you. Any questions before we close? Yes. Yeah. All of this is done by scikit-learn. When you call random forest.fit, this is what scikit-learn does, right? It builds the trees, it selects a subset of the features, points, whatever you prescribe, and then calculates the majority voting as well. Yeah. You guys were the optimizers in this case. Okay. Thank you so much for attending. Yep. Sounds good. Thank you.